In this presentation, we're going to start our study of simple machines, and we're going to talk about three of those simple machines: the lever, wheel and axle, and the pulley. All right, so what are simple machines? Well, simple machines make your life easier, okay? And they do that by manipulating the magnitude of force and distance, okay? And we're going to use that force and distance to do a variety of calculations here. So as we study simple machines, understand this. We're going to do a little bit of math. We're going to figure out how much easier these simple machines are making our life. All right, here's the three we're going to talk about today. The lever, right? On the left there, you see we typically think of levers as being straight. We have a little curved lever there. In the middle, wheel and axle. It's Ferris wheel. It's a wheel and axle. All right, and then a pulley. Okay, on the right there, you can see we have a pulley system here that's going to lift this airplane. Okay, here's our pulley. Okay, you cannot see the strands in that picture, but they are there. Now, there's a total of 6 simple machines. Here's the other 3. We'll talk about these at another time. Inclined plane over here on the left, roller coaster going up the inclined plane. The wedge, not the fireman. The wedge here is the tip of that axe right there. We have a wedge. And then we're going to talk about screws, okay? We'll talk about threads. The screw will be the most complicated type of simple machine that we do talk about. Now, these 6 simple machines make your life easier, all right? They make your life easier by creating a mechanical advantage, all right? Now, the MA, okay? There's going to be IMA and AMA. Right, those will be 2 subcategories of mechanical advantage. Okay, but in general, mechanical advantage is the ratio of the magnitude of the resistance and effort forces. So the resistance, let's say we are trying to hoist up that airplane in that previous picture. Okay, let me go back one more. The resistance is the downward force of the plane. Your effort force is whatever's pulling down on this pulley to raise this. Okay, that is the effort. Mechanical advantage will also take into account the ratio of distance traveled by the effort and the resistance forces. All right, and so these numbers, when we talk about mechanical advantage, are going to enable engineers, the designers of devices, to manipulate, as it says here, okay, to manipulate the speed, distance, force, and function of our simple machine. All right, so for example, here we have a box being pushed up an inclined plane. You might think of it as a ramp, okay, but it's really an inclined plane, okay? You have this box going up here. Now, that box vertically is only traveling upward this much, as you can see here with this box, okay? All right, so question here, all right? A mechanical advantage of 4 to 1, that's how you would say that. Mechanical advantage of 4 to 1 tells us what about a mechanism, okay? In terms of the magnitude of force, the effort to push that box up that ramp is 4 times less than the resistance of that box, okay? All right, so that ramp makes our effort 4 times less than if we were to just lift it vertically up, okay? Now, the distance traveled by the force. The effort force travels 4 times greater distance than the resistance force, okay? So here's the deal, all right? There's trade-offs. So the trade-off to making our effort less to move it up that ramp is that we have to travel a greater distance, okay? So our effort up this ramp is 4 times greater. Okay, let's say that is 20 feet. It's 4 times greater than the resistance. The resistance, as I stated at the beginning of the slide, the resistance is only going up this much. So if the effort is going and pushing that up 20 feet, the resistance is only going 5. Okay, the effort force travels 4 times greater of a distance. All right, now, when you're pushing something up a ramp, for example, you are doing work. The force applied on an object times the distance the object travels parallel to the force, okay? So down here we have the first equation that we need to write down and make sure we know. Work equals force times distance, okay? And the distance, that parallel component, is if I'm moving this box across the floor, okay, the distance I want to calculate is from here to here, all right, parallel to the force I'm exerting on it, okay? See this arrow? That's the force I'm exerting on it. It's parallel to this distance traveled, okay? Work equals force times distance. All right, now, the product of the effort times the distance, so the work, all right, will be the same regardless of the system mechanical advantage. All right, so let's talk about these ratios. One is the magic number, okay? It's our pivot point, it's our turning point, meaning this. If our mechanical advantage is greater than 1, okay, less effort is required to overcome the resistance, okay? All right, now the trade-off is your effort, a greater effort distance is required to overcome the resistance, like that inclined plane example. But if your mechanical advantage is greater than 1, it's going to be easier to move something. It's going to make your life easier, okay? On the other hand, if the mechanical advantage is less than 1, all right, it's going to require a greater force to overcome the resistance, all right? But it'll require less effort distance to overcome the resistance force. Now, there are some examples where we do want a mechanical advantage less than 1, okay? And we'll talk about that. But most of the time, you're going to want an MA greater than 1. All right, and the last point there, your mechanical advantage can never be negative or 0. All right, so let's start off here with IMA, ideal mechanical advantage, okay? And so you want to write down this equation. IMA is equal to D sub E divided by D sub R. Those capital D's and their subscripts mean this. D sub E means the effort distance. D sub R means the resistance distance. Okay, now, when I was learning this, we called it the I'm a deer equation. See it? IMA, the IMA, deer, D-E-D-R. I'm a deer. Okay, now, this is a theory-based calculation. We're not going to take friction into consideration, right? So this is like an ideal environment, ideal mechanical advantage, IMA. It is the ratio of the distance traveled by effort, D sub E, divided by the resistance distance, okay? Using efficiency and safety factor design calculations, okay? So this is the equation for ideal mechanical advantage. It is theory-based. We don't do any trials. We don't, like actually push the box up the ramp. It's pure theory, okay? On the other hand, we have AMA, actual mechanical advantage. This is where you do the thing. This is where you actually perform the experiment because you have to measure the forces, all right? So AMA, okay, actual mechanical advantage, equals the resistance force, that's F sub R, resistance force, divided by the effort force, okay, F sub E. Okay, so we want to know this equation, okay? Called this, when I was learning it, the America free equation. AMA, America free, FRFE. America free, see it? Now here, frictional losses are taken into consideration because we're going to use a device to measure the forces. And there'll be a new type of device that we will use, that you'll use in class here with some software to measure effort force, okay? All right. All right, so you may be asking yourselves, AMA and IMA, okay, well, I thought we were talking about levers and wheel and axles and pulleys, and we are, okay? So what we want to do, we kind of want to introduce AMA and IMA because we're going to calculate the AMA and the IMA of these different simple machines. Okay, so let's talk about our first simple machine, the lever. Okay, you see the definition of a lever there. There's three different types. Okay, there's three different types. All right, so let me show you what's going on here. Okay, this middle lever. Okay, here's what you're looking at. This part right here. Okay, all right, we call that the fulcrum. Okay, it's right in the middle on that one, or I should say it's between the effort force and the resistance force. This is the fulcrum here. Okay, and this is the fulcrum here. Okay, but there's three types of levers. Okay, we call them first class, second class, and third class levers. Okay, and so we're going to talk about each one of those here. All right, the first class lever. Okay, the fulcrum is located between the effort and resistance forces, not right in the middle. Okay, it's just between. It could be closer to one than the other. All right, so here in this diagram, here's your fulcrum. It is between the effort force and the resistance force. An example of a first class lever is a teeter-totter. Okay, that fulcrum, if you and a buddy sit on each end, all right, one of you is the effort, one of you is the resistance, the fulcrum's in the middle. So a teeter-totter is an example of a first class lever. Okay, the effort and resistance forces are applied in the same direction. Okay, so both forces here in all of these three examples, all right, are going down. Okay, all right, now if the fulcrum is exactly in the middle, your mechanical advantage is equal to 1. Okay, if your fulcrum is closer to the resistance, you have a mechanical advantage greater than 1. Okay, it's going to require less effort to lift that resistance. All right, but on the other hand, if your fulcrum, let me get that out of there so that goes away. If your fulcrum is closer to the effort, your mechanical advantage is going to be less than 1. So it's going to take more effort to lift this resistance load. Okay, and so understand this. This is the only class of lever that can have a mechanical advantage greater than or less than 1. Okay, greater than or less than 1. Okay, you got to remember that. Okay, first class levers are the only lever that can have a mechanical advantage greater than or less than 1. Okay, teeter-totter. Second class levers. Okay, so now with the second class lever, we're going to move the fulcrum. Okay, it's going to be located at one end of the lever. Okay, one end of the lever. This time the resistance is between the fulcrum and the effort. Okay, the resistance is between the fulcrum and the effort. And your forces are in opposite directions. Okay, so unlike the first class where both forces were down, the second class, the resistance in this case is going down and the effort is going up. Your forces are in opposite directions. Okay, now this type of lever always has a mechanical advantage greater than 1. Okay, again, this type of lever always has an MA greater than 1. An example of this, of a second class lever, is a wheelbarrow. Okay, so in that wheelbarrow, all right, so an example, like I said, of second class lever is a wheelbarrow. I put a wheelbarrow up here for you. And here's where the fulcrum and the effort and the resistance are. So the fulcrum's the wheel. Okay, the fulcrum's the wheel. The resistance, okay, the resistance would be the load in the wheelbarrow, dirt, bricks, whatever you're hauling. And that force is pointing down. Your effort is you holding the handles here. And you're lifting, so your effort's up. Okay, so fulcrum, resistance going down, effort going up. Second class lever. Third class lever, okay? Similar to the second class lever. Let me go back 1 second. Second class lever always has a mechanical advantage greater than 1. Okay, always greater than 1, right? Now, third class lever. Just like the second class, the fulcrum's located at the end. But the difference here is the resistance and the effort have changed spots. Now the effort is in the middle. It's between the resistance and the fulcrum. Okay, so they've just flip-flopped. Second and third class levers are very similar in that the fulcrum's at the end, but where the resistance and effort forces are different. Here with the third class, the effort is between the resistance effort and the resistance force and the fulcrum. Okay? Still, the effort is in opposite directions. Okay? So the only type of lever where the force is in the same direction is on the first class lever. Second and third, forces are in opposite. Okay? This always has a mechanical advantage less than 1. Okay? This always has a mechanical advantage less than 1. An example of a third class lever, what you see here is these tweezers. Okay? The fulcrum is down here. All right? There's your fulcrum where the tweezers are connected. Okay? The effort is when you squeeze in. Okay? That's your effort force. Your resistance is whatever you're grabbing here. The resistance, so trying to get a splinter out of your finger. The resistance, if I have a little splinter in here, it is pushing out, okay, on the tweezers, okay, in the opposite direction of me pushing in with my effort here. All right, and just to emphasize this, always has a mechanical advantage less than 1. All right, new word for us, moment. Okay, moment is the turning effect on a force about a point equal to the magnitude of the force times the perpendicular distance from the point to the line of action from the force. It's a lot. Understand this, moment, turning effect, okay? All right, so if I were to press down on this forever and ever, okay, ignore gravity, this thing would go around in a circle. Same thing here. It would we would go around this in a circle, okay? A turning effect, okay? Here's the equation. M for moment equals distance times force, okay? Your moment or your turning force equals distance times force, okay? Now, here's another new word for you, torque, okay? Torque is a force that produces or tends to produce rotation or torsion, okay? Moment and torque are synonymous, okay? They're the same thing. Rotation, turning effect, torsion, okay? We're rotating, moment, torque. And there's your equation for it right there in the middle, okay? So with levers, let's calculate, let's do a moment calculation here, okay? All right, calculate the effort moment acting on the lever, okay? So the effort moment means we're going to use the effort force, okay? So here's your equation. Moment, or effort moment, equals the distance times the fulcrum. The distance is from the effort force, because we're doing the effort moment, to the fulcrum. All right, so the distance, 5.5 inches, okay? The force, okay, is your effort moment, okay? Your force here is your effort force, okay, because we're talking effort moment, okay? So effort moment equals that 5.5 inches times 15 pounds, okay, for a total of 82.5 inch-pounds, okay? Now, side note on moments or rotation or torque, okay, is this. If when we rotate, as we would with the effort force, all right, and we would go in this direction, okay, to rotate, that is counterclockwise, okay? That is counterclockwise. Counterclockwise, positive force, okay? Counterclockwise, positive force. That's why we are a positive 82.5. Counterclockwise, positive, okay? On the other hand, if we were finding the resistance moment and we would push down and rotate this way, that's clockwise, okay? That's a great W. That's clockwise. Clockwise moments, negative force, Okay? So if we knew the distance here and we knew the resistance force here, okay, when we would multiply them together, this resistance force would be negative. So we would get a negative moment, okay? But just know this, clockwise, negative moment. Counterclockwise, positive moment. All right, next. Now, let's say our lever isn't moving. You and your buddy are on the teeter-totter and it's still, okay? That means all the moments on that lever are zero. It's not rotating. So we say the lever is in rotational equilibrium, right? And so here's kind of the real wordy summary that I just said, okay? Rotational equilibrium, the state in which the sum of all the clockwise moments equals the sum of all the counterclockwise moments about a pivot point, or with our lever about a fulcrum. We're not moving, okay? We are not moving, all right? Rotational equilibrium, okay? So let's use this idea of rotational equilibrium to figure out the resistance distance here, all right? Figure out the resistance distance, all right? So if this lever is in rotational equilibrium, that means all the moments are equal. Our effort moment is equal to our resistance moment, okay? And if I added them together, they equal zero. And that makes sense, right? Because this effort is counterclockwise. It would be positive. If I added it to the resistance moment, which would be negative, they would equal zero, okay? So let's use that fact, rotational equilibrium, to figure out the resistance distance. That's where our question mark is. We know that the resistance force is 36 2/3 pounds, okay? Or 0.66, 36.66 pounds. We don't know the resistance distance. We know the effort distance is 5.5 inches and the effort force is 15 pounds, okay? So here's what we got. Effort moment equals the resistance moment, okay? So when your effort equals your resistance, in this case, on this first class lever, we are in rotational equilibrium. We're not moving. You and your buddy are on that teeter-totter. Nobody's moving, okay? So here's what we got. Effort moment. So this left side over here, all right, I'm going to draw on this a little bit, okay? Effort moment. 15 pounds is your 15 pounds of force here. Your 5.5 inches is your 5.5 inches here, okay? That's equal to, all right, your 36 and 2/3 or 36.66, okay, resistance force times your resistance distance, which we don't know. That's your question mark. Okay, now you'll notice, all right, while it is going clockwise, it's not negative, but that's because it's on the other side of the equation, okay? All right? If I did it this way, effort moment, it's positive, minus resistance moment equals zero. That's another way to do it, okay? There it's negative, all right? Continuing on, all right? When you multiply the 15 times the 5.5, you get 82.5 inch-pounds, okay? On the other side, we have an unknown, so it's still 36.66 times the resistance distance, all right? Okay. What we have to do next is divide each side. So in this step here, we're dividing each side by 36.66. So it ends up being 82.5 inch-pounds divided by 36.66 pounds equals your resistance distance. And your answer, 2.25 inches. Okay, your answer is 2.25 inches. Okay, now let's talk units here. Okay, so with my units, how do we get from these pounds and pounds down to inches at the end? Well, when you multiply pounds times inches, you combine them. inch-pounds. Okay? You combine them. When you divide, right here, inch-pounds divided by pounds. Okay, so we've got inch-pounds divided by pounds. What happens is things cancel out. Okay, so your pounds cancel out, leaves you with inches. And that's why our answer is in inches. Notice as we went through this, we included our inches in every step of the calculation. Make sure you include your units in every step of the calculation. Okay? All right, lever IMA. Okay? Deer equation. Both effort and resistance forces will travel in a circle if unopposed. We already know that. It's going to turn. All right? So your IMA, there's the circle. Yay. All right? All right, now, there's a whole bunch of stuff there, okay, to show you how we get the effort distance and the resistance distance, okay? Here's the easy part, okay? Here's the easy part. The IMA of a lever is your effort distance. Let me get this out. My effort distance, okay? Your effort distance is the distance from the effort force, went a little far, to the fulcrum. Okay, that's your effort distance. That's what you would put in the numerator. That's what you would put here. Okay. Resistance distance, your denominator, what goes here, is the distance from the resistance force to the fulcrum. Okay. Ignore all this stuff. Okay. Ignore all that. IMA equals the effort distance from the effort to the fulcrum divided by the resistance distance from the resistance force to the fulcrum. Easy enough. All right, that's IMA. Now, AMA. Okay, with AMA, we actually have to have some calculations, okay? Or we have to be provided some forces given to us. And here we are. So AMA equals the resistance force over the effort force. The resistance force is 32, okay? The effort force is 16, okay? So 32 pounds divided by 16 pounds. The pounds cancel each other out, okay? AMA is 2 to 1, okay? AMA is 2, okay? That's another way to just write it, okay? Now, IMA, effort distance, 5.5. Resistance distance, 2.25, okay? 2.44 to 1, or just 2.44, okay? Now, notice the units for both of these cancel each other out. AMA and IMA are unitless. There will be no units on AMA and IMA. Okay. Why is the IMA larger than the AMA? Because it doesn't take friction into account. Friction brings our number down. All right, efficiency. How efficient is our machine? Okay. All the efficiency is the ratio of AMA to IMA. So here's another equation for us. Percent efficiency equals AMA divided by IMA times 100. Okay, so make sure we get that equation down. All right, so what's the efficiency of the lever on the previous slide? Okay, AMA was 2, IMA was 2.44. So it's just 2 divided by 2.44 times 100, 82% efficient. Know this, no machine is 100% efficient. We are always going to lose something as that machine works. Whether it's to friction, whether it's to heat, we're always going to lose something. Okay. All right, wheel and axle. Okay, you probably got here today on a wheel and axle. All right. A wheel is just really a lever arm fixed to a shaft called an axle. Okay, it's a form of a lever. All right. Okay, as you can see here, fulcrums here, okay? We have the effort here and the resistance here, okay? So the wheel and axle move together as a simple lever, okay, to move something, okay? Now, it's important to know what is applying the effort and what's applying the force, the wheel or the axle. So sometimes this arrow will be the resistance. Sometimes this arrow will be the effort. Sometimes this arrow will be the resistance. Sometimes this arrow will be the effort. Okay. All right. So example, let's see here, middle one. It's like it's on a stove. Okay. We're getting ready to turn the burner on. Middle right here. I have a wheel because I'm turning the knob. Okay. The wheel is where the effort is. The axle is where the resistance is. Okay. Same thing here. I'm turning this wheel. All right. I've got a valve. There's an axle going in here. All right. The effort's on the outside. The resistance is on the inside. Same thing here. Okay. I'm using my steering wheel to turn an axle. Effort would be here. Resistance would be on the inside. All right. So for wheel and axle IMA, what are the two distances we're going to use? Well, it depends where your effort is. It depends where your resistance is. Okay. So let me bring up a bunch of stuff here. Okay. Don't worry about any of this. Right? This is just a bunch of stuff. All right. Talking about circles and all that fun geometry. Okay. Just understand this. Okay. So what is the IMA of the wheel if the axle is driving the wheel? So if the axle's driving the axle is where your effort is. So our effort's in here. Our resistance is out here. Okay. So your effort is the diameter. Okay. Your effort is the diameter of the axle. Your resistance is the diameter of the wheel. Okay. Effort distance over resistance distance. Okay. All right. Effort is at the axle. That diameter is 6. Resistance is at the wheel. That diameter is 20. So our IMA is 0.3. All right. 0.3 to 1, 3 to 10. I would want you to write this as 0.3. This is fine. Our IMA is 0.3. Now let's flip it. What is the IMA of the wheel if the wheel is driving the axle? So this time, your effort is out here. Your effort is with the wheel. Your resistance is with the axle. So your effort distance is the 20. Your resistance distance is the 6 because now the wheel is driving the axle. And you can see the difference here. All right. This time, 20 inches divided by 6 inches gives us an IMA of 3.33. Okay, so it's a little bit easier for us if we use the wheel to drive the axle rather than the axle to drive the wheel. All right, now AMA with our resistances. Okay, same thing. We got to know where the effort is and where the resistance is. Okay, so what is the AMA if the wheel is driving the axle? So the wheel is where the effort is. The axle is where the resistance is. All right, so we have resistance force over effort force. So if our resistance is at the axle, that's 200. If our effort's at the wheel, okay, effort's at the wheel, that's 70. Okay, so it's just 200 divided by 70, 2.86. If we flip-flop it, oh, I'm sorry, we're not going to flip-flop. Let's find our efficiency. Okay, what is the efficiency of the wheel and axle assembly? Okay, so percent efficiency, remember, is just AMA over IMA times 100. Okay, so 2.86 divided by 3.33 times 100, 85.9%. Okay. The biggest thing with the wheel and axle is we know where the effort is and where the resistance is. All right, pulleys. Okay, a pulley is also a lever consisting of a wheel with a groove. Okay, and it's used to change the direction and magnitude of a force. Okay, so a couple things about pulleys and pulley IMA. Okay, a fixed pulley. Okay, so fixed pulley is this over here because it is attached. It doesn't move like there is like a ceiling here and that pulley's attached. All right, and we're trying to lift this 10-pound weight off the ground. We're here and we are pulling really long arms down to lift this force up. That's a fixed pulley. Now, to figure out the IMA for this fixed pulley, no math, it's 1. It's automatically 1. Okay. Movable pulley. Okay, so now our thread is attached to the ceiling here. All right, we're up here. Okay, we're up here and we're pulling up this time. All right, to move the force this way. Okay, so a movable pulley, because this pulley is not attached to anything, automatically has an IMA of 2. Okay. Okay, so quick introduction to pulley IMA, right? 1, fixed. 2, movable. All right, now, won't always be that simple, of course, okay? Pulleys in combination, okay? So here we have fixed and movable pulleys, okay? Up here at the top, we have a fixed pulley. And we have a movable pulley. I'm sorry, we have 2 fixed pulleys here. Movable pulley, okay? Okay, so when they're in combination, how we find the IMA, that's what this slide is all about, is the following. If we have a single rope or cable threaded through all the pulleys, which we do, okay, we're starting here, and we're going up, around, and around, and up, and around to here. It's a single strand, okay? What is the IMA of this pulley in this situation? All you have to do is count the number of strands opposing the force of the load, okay? So here's what we mean. The load, all right, is the force of the load's going down, okay? The force of the load's going down. Here, on this strand, we're standing here pulling, let me do this. We're standing here pulling down on this strand, okay? All right, we're standing here pulling down on this strand, okay? So it says count the number of strands opposing the force of the load. So I'm not going to count this one because it's going in the same direction as the load. But I am going to count everything else. 1, 2, 3, 4. What's the IMA of the pulley? 4. Okay, those 4 strands. Those 4 strands are opposing the load. So the IMA is 4. Okay. All right. So here's the deal with pulley IMA. Okay. If you have a single fixed pulley, it's just 1. If you have a single movable pulley, it's 2. If you have pulleys in combination, count the number of strands opposing the force of the load. That's your IMA. Okay. Now we're going to assume that all our strands are vertical. Okay. When we start to get angles, we have to use trig. That doesn't happen for a while. Okay, so assume everything's vertical right now. All right, so what is the IMA of this pulley system? Now, the difference between this and this is that there's a single strand here. Here I have multiple strands. So we're going to look at each one individually. Okay, we're going to look at each one individually and we're going to multiply them together. So the IMA total is the product of the 3 different IMAs because we have different strands in this system. Okay, I have 1 strand here, okay, at this pulley. This is a movable pulley. Okay, I have another strand here with this movable pulley. And I have another strand here with this movable pulley. Okay, so that's different. We don't count the threads. We only do that when we have a single thread. Here we have different. So we're going to take each pulley individually. All right, so this pulley is a single movable pulley. What did we say about the IMA of that? 2. Okay, IMA is 2. All right, here, Think of it on its own. Single movable pulley, IMA is 2. Third one, single movable pulley, IMA is 2. For the system then, we are going to multiply those three together. 2 times 2 times 2 is 8. The IMA of that system of pulleys in combination with separate ropes or cables is 8. Okay? The IMA. Now, AMA. Okay? A little simpler. Because we're going to deal with the forces, don't have to count anything. Okay? What is the AMA of this system of pulleys? Okay? Effort force right here. I'm pulling down 230 pounds. Resistance force, I'm trying to lift an 800-pound weight. Okay? So resistance, boom, numerator. Effort, boom, denominator. And then you just have to divide them. Okay? 800 divided by 230. Units cancel out. 3.48 is all I need. Okay? AMA is 3.48. So what's the efficiency of this pulley system? AMA over IMA. AMA, we're going to steal from this slide, that 3.48. The IMA, okay, remember the IMA, we figured this out on a previous slide, right? But let's just revisit that. The IMA for a combination of pulleys with a single strand, you just count the strands opposing the force, okay? So 1, not that one. Get my pen out here. Okay, 1, 2, 3, 4. Not this one, because it's going in the same direction as the resistance. Okay, so this is 87% efficient. Okay, some common misconceptions. Okay, got 2 more slides here. Is that angles don't matter? They do, all right? But we're going to need trig to figure that out. But right now, we're just going to assume everything is going vertically. Okay. Another common misconception is count the effort strand if it pulls up. Not true. Effort strands could pull down. Okay, they could pull down. Right. So sometimes, okay, we could pull down to lift a load. All right. And so that's all about pulleys. All about pulleys and levers and wheel and axles. And those are all grouped together because all 3 of those are really just levers, okay? Got to understand the IMA and the AMA, how to figure those out, and know those equations as well as efficiency. And that's the end of the lecture.